We have a half-century of physical exploration telling us we know our nearest neighbor. Decades of orbiting spacecraft have mapped its craters, ridges, and valleys in exhaustive visual detail. We have even brought physical samples back to Earth. But these Apollo rocks are highly localized snapshots. They tell us exactly what the dirt is made of in a few specific parking spots. Despite the iconic photos and carefully cataloged rocks, our grasp of what the entire moon is actually made of is full of holes. The hard truth is, even today, humanity does not possess a complete global map of the moon's chemical makeup. While this overhead view shows high-definition terrain, our chemical data for these areas is severely lacking. The blind spots are massive, especially near the dark lunar coals. We can't solve this by sending rovers to scoop dirt from every square inch. The surface area is simply too vast for physical collection. Without a geochemical map, geologists are missing the crucial data required to figure out exactly how the moon formed and evolved over billions of years. To scan the lunar chemistry from orbit, scientists use remote sensing. But to see what the surface is made of, you need a powerful external light source to hit it first. Regular visible light won't work. The process requires the most violent eruptions of radiation in the solar system, solar flares. The mapping method relies on X-ray fluorescence. Solar radiation strikes lunar dirt, exciting the atoms. They react by firing unique X-rays into space. Elements like iron and silicon emit specific wavelengths. An orbital detector reads these signatures, identifying the surface below. The sun provides the perfect flashlight. The failure point has always been building an orbital tool capable of catching those returning X-rays. Historically, orbital mapping missions face a strict timer. They have to wait for random solar flares to happen, and all the while, their sensitive detectors degrade from constant cosmic radiation. Making matters worse, traditional X-ray observatories are huge, heavy pieces of machinery. They are completely impractical to strap to an agile satellite orbiting the moon. Researchers at Tokyo Metropolitan University bypassed this problem by looking at Earth. They took a compact X-ray telescope, originally designed to study our own magnetic field, and repurposed it for lunar orbit. This new design weighs less than 10 kilograms. Furthermore, it has already been tested in radiation conditions far harsher than anything it will experience around the moon. By abandoning heavy, room-sized architecture in favor of cheap, microscopic durability, scientists finally have the engineering required to survive a long-term mapping mission. To test if this tiny device could pull it off, the team ran a numerical simulation, factoring in about 300 solar flares a year. The model showed that one 10-kilogram telescope operating for 2 years could map 5 crucial elements, like oxygen and aluminum, across the entire globe. There is a constraint. A single lens would yield a map broken into a grid, where each block is 70 kilometers across. Because the technology is so small, there is a scalable solution. You mount a 5x5 array of 25 microtelescopes onto a single satellite. This array cuts the mapping time down to 1 year and sharpens the resolution to 30-kilometer blocks. Given 2 years, it becomes sensitive enough to detect trace elements like sodium. By combining a swarm of these microscopic sensors into one networked toll, scientists can solve a mapping problem that has stalled lunar geology for decades. If this mission flies, the resulting data will be the first complete map of elemental abundance ever produced for the moon. With that chemical map, geologists can accurately reconstruct the chaotic history of the lunar surface, providing a direct window into how our own planet formed. After millennia of staring at the cold exterior of our nearest neighbor, a 10-kilogram device is finally going to let us look inside.